Okay, let's dive right into one of the most exciting and, let's be honest, mind-bending topics in technology today: quantum computing. This is a field that isn't just about making things faster. It's about completely rewriting the rules of what's possible.
For decades, these machines, these absolute behemoths, have been the undisputed champions. They've been the workhorses behind everything from weather forecasting to designing new medicines. They are the pinnacle of classical computing. So you gotta ask, right? If these machines are so powerful, why are the biggest names in tech pouring billions of dollars into a frantic race to build something else? Well, it's because this isn't a race to build a better supercomputer. It's a race to build a fundamentally different kind of machine. And the answer is right there, in that one word: quantum. We're talking about a leap in computation so huge, it promises to solve problems that aren't just hard for our current computers, but are literally impossible for them to solve, ever. This whole race really exploded into the public eye with a dramatic showdown between two of the heaviest hitters in tech. It started with a huge claim from one and a very public, very fast rebuttal from the other. You could almost hear the starting gunfire. So here's what went down. Back in 2019, Google basically declared victory. They said their quantum processor, Sycamore, did a calculation in about 3 minutes that would take the world's best supercomputer 10,000 years. But then IBM immediately fired back and said, hold on a second. We think our supercomputer could actually do that in just 2.5 days. Now, who was right is almost beside the point. The fact that this argument was even happening told the world one thing: the quantum era was here. And at the very heart of this debate is this phrase: quantum supremacy. It's the goal line everyone is sprinting towards. It's that crystal clear moment when a quantum computer does something useful that a classical computer, for all practical purposes, just can't. So, to really get what this race is all about, we need to understand why. Why are we pushing past the amazing technology we already have? What's the fundamental problem we're trying to solve here? Well, it all comes down to something called Moore's Law. For 50 years, it was the engine of progress. We just kept making transistors smaller and smaller, packing more power onto our chips. But now, we've hit a wall, a physical wall. We're trying to build things at the scale of individual atoms. And at that level, the normal rules of physics just stop working, and the weird, wonderful rules of the quantum world take over. And this is where things get really wild. You see, your computer, your phone, they all work with bits. And a bit is like a light switch. It's either on, a 1, or it's off, a 0. Simple. But a quantum bit, or a qubit, well, it can be a 1, it can be a 0, or, and this is the mind-bending part, it can be both at the exact same time. This incredible property has a name: superposition, and it is the secret sauce. Because a qubit can exist in multiple states at once, a quantum computer can explore a huge number of possibilities simultaneously. It's like, instead of trying to find your way through a maze by taking one path at a time, you could explore every single path all at once. It's the ultimate form of parallel processing. Now, if you think superposition is strange, just wait. There's another quantum property that's even weirder. So weird, in fact, that it famously made one of the smartest people in history deeply uncomfortable. It's called entanglement. Here's the best way to think about it. Imagine you have 2 coins, and they are magically linked. If you flip them and one lands on heads, you know instantly that the other one, even if it's on the other side of the universe, has landed on tails. Their fates are intertwined. This is the idea that bothered Albert Einstein so much that he called it spooky action at a distance. It seemed to break the universe's ultimate speed limit, the speed of light. I mean, how could one particle instantly know the state of another one, billions of miles away? It just goes to show how truly counterintuitive the quantum world really is. So, we've got superposition, we've got this spooky entanglement. These are incredible ideas, but you're probably asking, okay, so what? What's the payoff? What are the real, actual things we can do with this that makes it so important? Well, first up, we can take that spooky entanglement and turn it into the ultimate security system. We can create communication channels that are, by the laws of physics, completely unhackable. If anyone even tries to eavesdrop on the message, the very act of observing it breaks that delicate entanglement. And poof, the connection is severed, and everyone knows there's an intruder. It's like having a security system built into the fabric of reality itself. But here's the other side of that coin. Just as quantum physics can build the perfect lock, it can also build the perfect skeleton key. There's a quantum program called Shor's algorithm, And it's designed to be incredibly good at one specific thing, cracking the kind of encryption that protects, well, pretty much everything online, your bank account, your emails, all of it. This is the great double-edged sword of the quantum age.
Now, beyond the spy movie stuff of codes and ciphers, this is where the real revolution could happen. Because nature itself is quantum. Simulating it on a classical computer is incredibly hard. But for a quantum computer, it's what it was born to do. This means we could design new life-saving drugs, atom by atom. We could invent materials that conduct electricity with zero resistance, or create new catalysts to pull carbon right out of the atmosphere. We're talking about a new era of science.
Okay, unhackable communication, revolutionizing science. It all sounds amazing, and it is, but let's take a deep breath for a second and ground ourselves in a quick reality check. We've talked about the incredible potential, but where are we right now on that journey? I think this quote from MIT's Will Oliver just says it perfectly. We're at the Kitty Hawk moment. The Wright brothers proved that powered flight was possible, but that first flight was just a hop, skip, and a jump. It was a long, long way from a Boeing 747 crossing the Atlantic. We've proven the principle, but the engineering challenge ahead of us is enormous.
The technical term for where we are right now is the NISQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale is good. It means we have processors with 50 to a few hundred qubits. But the key word there is noisy. These qubits are so incredibly delicate that the tiniest vibration or change in temperature can throw off their calculations. It's like trying to solve a really hard math problem on a whiteboard while someone is constantly shaking it. The errors add up fast. But even though we're in this early, noisy days, the implications are so huge that we can't afford to wait. People are already planning and preparing for what comes next, for what a post-quantum world will actually look like.
Remember that skeleton key, Shor's algorithm? Well, that threat is so real that governments and companies are already in a mad dash to develop what's called quantum-safe cryptography. The whole goal is to invent new ways to protect our data that will be safe from both today's supercomputers and tomorrow's quantum computers. This isn't theoretical, this is happening right now.
So that's where we are. We're standing right at the dawn of a completely new computing age. The potential to change medicine, science, and our entire digital world is absolutely real. The principles are proven, the race is on, and really, the only question left is the one right here in front of you. What are we going to build with it?